Okay, hi guys, welcome to Biology Online with Henny van Vieren. Good afternoon guys, or good morning, or even good evening, depends on what time you're watching this. But today we're going to talk about passive transport across the cell membrane. This is how we move things through the cell membrane, either in or out. So some things we need to get rid of out of a cell, some things we need to bring in. So this is all about passive transport. Now, what is the difference between passive transport and active transport? So passive transport is where there is no use of ATP. In other words, it will always go down a concentration gradient, okay? And we'll get into more detail as we go along. So please follow along. The document on the OneDrive is called Cell Processes, Passive Transport, and you can make notes in that if you like. So here we go. So passive transport across the cell membrane. So number one, what is the function of the cell membrane? Remember, this is a selectively permeable membrane. In other words, it keeps the wanted stuff in and the unwanted stuff out. It lets the wanted stuff in and lets the unwanted stuff out. So it's a gatekeeper and it's a fence. So the cell membrane separates the inside from the cell with the outside. And if you think about an aquarium fish, if we put a freshwater fish into a saltwater aquarium, what's going to happen? A lot of the water will flow out of the fish, okay? But and that's all part of osmosis, but that fish will most likely die. There's only a few types of fish that can survive in both fresh and in salt water. We talked about the bull shark, we've talked about our local New Zealand eels and the salmon and so forth. Okay, a selectively permeable membrane is a membrane that will only allow certain molecules or ions to pass through it. This can be due to diffusion, facilitated transport, active transport, and occasionally things like other active transports like phagocytosis and pinocytosis and so forth. So we will get to that. But when we talk about our passive transport, the first one that we need to look at is the simpler versions of this, okay? So passive transport is the movement of particles or water across a cell membrane without the need for energy input. In other words, no ATP, okay? The rate of passive transport depends on the cell membrane permeability. So when you think about this and you look at this cell membrane over here, you will see that the more channel proteins you have, the faster it will be. The more holes you have in a sieve, the faster it will be, or the bigger the holes. So the more permeable it is, the faster it will be. But also the concentration gradient, in other words, the concentration of the molecules on the other side of the membrane. Because of that concentration gradient, you will have passive transport. Now, the permeability of our membrane. What things are permeable? Now, lipids or lipid products can actually go through our cellular membrane. They don't need to go through channel proteins and so forth. The other things that can go straight through are oxygen and CO2 and water. All of those can go through passive transport. But we also have things called aquaporins. Let's think about that word for a moment. Aqua means water. Porin is a pore, so it is a little water channel, water hole, okay? And that is specifically designed for water to go in and out of the cell, even though water molecules can go through the cell membrane. Now we've got simple diffusion, we've got facilitated diffusion, we've got filtration and osmosis. When I made this slide, I don't think filtration should be part of that. So just simple diffusion and facilitated diffusion and osmosis. Now, what are the difference between these things? So the first one we're going to talk about is the channel protein. I've just talked about a channel protein is a membrane protein fixed in shape that has a water-filled section which selected hydrophilic molecules or ions can pass through. This is facilitated diffusion. What does facilitated mean, guys? Your parents facilitate your learning. They don't do it for you, In other words, it makes it possible. Facilitate diffusion simply to make it possible. Okay, doesn't necessarily need energy to do that, but it needs to make it possible. So when we talk about an aquaporin or just a channel protein like this one is, they will simply facilitate by allowing water-soluble molecules to actually go through. All right, now your so it'll go through via the concentration gradient. So I hope that makes sense. So it facilitates the transport. We talked about aquaporins already. So here we have a carrier protein. Now a carrier protein is different. It's a type of membrane protein that changes shape to allow the passage of ions. So in other words, you can see this green, sorry about that, you can see this green molecule of glucose, and you can see the other molecule. Now, when your other molecule actually goes into this, it changes the shape of the protein, and then it is ejected on the other side. And as it is ejected, the protein will reopen on this way. So it goes in, it changes its shape, and it pops out the other side. So it's kind of like a rotating gate, or you've all seen those at bus stations and so forth. So there you go. Here's a video specifically talking about diffusion and going from a high concentration area of high concentration of water or high water potential. In other words, it's got a low concentration of solute to an area of high concentration of solute. Okay, so just have a look here. Oopsie.
Molecules dissolved in a solution are in constant random motion due to their kinetic energy. One result of this motion is that dissolved molecules become evenly distributed throughout the solution. This tendency of molecules to spread out is an example of diffusion. But how do these molecules come to be evenly distributed? Let's start with a beaker of plain water. What will happen if we now add a lump of sugar to the water? A lump of sugar is composed of many individual sugar molecules, and even as a solid lump, the individual sugar molecules are in motion. When the lump is dropped into the water, it begins to dissolve. Individual sugar molecules move randomly and constantly from the area where they are common to the area where they are scarce. This type of motion, when molecules move from areas of their higher concentration to areas of their lower concentration, is called diffusion. Diffusion continues until all the sugar molecules become evenly dispersed throughout the beaker. The rate of diffusion is affected by temperature, size of molecules, and the steepness of the concentration gradient. Although not specifically shown in this animation, this is one of the processes whereby materials are exchanged between a cell and its environment.
Movement of molecules from an area of high concentration to an area of low concentration. This is very important. Okay. You'll remember that in class we also looked at the plasmolysis and how the water moved out of these cells when we added salt water to it, and that's the part of diffusion that we're going to be looking at. So all molecules have kinetic energy. It's called Brownian motion, and basically you can see here where the blue is added, it's first an area of high concentration of solute to an area of low concentration of solute. So that is diffusion. Diffusion is the net movement of molecules or ions from a region of high concentration to a region of lower concentration. The molecules move down the concentration gradient and will continue to spread until an equilibrium is reached when there's no net movement of molecules. Equilibrium means your movement in one direction is going to be equal to someone else's movement in the other direction. Or for the chemists out there, equilibrium is when you have a reaction going from product to reagent. From reagent to product. There's equal amount of molecules then running in the other direction from reagent back to product. Okay, so that is equilibrium, equal on both sides. So our rate of diffusion is affected by four things: the surface area, which we've learnt about in gaseous exchange, and that's why we all need a large surface area, and that is what COVID-19 attacks, is your surface area of your lungs, so it makes it more difficult for you to breathe. So hence why we need to stay safe. Okay. Higher temperatures give the molecules more kinetic energy. Also the type of molecule. So the type of molecule, the bigger the molecule, the slower it will diffuse. Okay, that's just a function of a very large molecule. And then the steepness of the concentration gradient. In other words, if you have a very high concentration versus a very low concentration on the other side of your selectively permeable membrane, it will be a much faster rate than if you have a little bit more versus a little bit less. Okay, and that's a slow rate of diffusion or a less steep concentration gradient. You can think of it as a slide. Again, here we have water molecules, and this is a selectively permeable membrane. Now, because there's more solute on this side, in other words, in this case it's sucrose, because there's more sucrose on this side, the water will be drawn towards that. Now, osmosis is the specific diffusion of water. It's the net movement of water from an area of high water potential. The chemists don't want us to say a high water concentration. It's called a high water potential to a region of lower water potential through a selectively permeable membrane. Okay, so you need to be able to say that off by heart. Osmosis is the movement of water from an area of high water potential to an area of low water potential through a selectively permeable membrane. So if this side was on the inside of the cell, and you take a cell and you actually put it into pure water, the water will rush in because there's more dissolved solutes on the inside of your cell. Now, for those of you who wear contact lenses or know somebody who wears contact lenses, you know that they actually need to use saline to help with their eyes. And saline is 9 grams per liter of water. So there's 9 grams of sodium chloride or 9 grams of salt in a liter of water, 0.9%. And what then happens is that the concentration inside your cells of dissolved molecules and the concentration in the saline, which they then put in their eyes, are going to be the same. Otherwise, every time, if you just keep it in normal water and you add normal water to your eyes, we all know how that feels if you open your eyes underwater. That potential pain that you feel is because water is streaming into your cells of the cornea, and that can potentially damage them if they are left there for too long, because if we leave them for too long, those cells will swell up and eventually they can actually burst. We'll have a look at that soon. Okay, we've said this already, movement from a high concentration to a low concentration. Now this is specifically talking about the solute, not about water. And this is a passive process. It does not require energy. As long as there's a gap for it, a channel protein or something, it will allow it to go through. Okay, we talked about breathing already, and specifically regarding the breathing, you have a high surface area or a very large surface area, and as the air comes in, it's full of oxygen. The blood is not full of oxygen, so the oxygen will simply diffuse from inside the alveolus out into the blood. The CO2 is much higher in your blood and consequently will diffuse out of the blood into the alveolus. Okay, so here we have simple diffusion. As you can see, lipid soluble molecules. Remember, like will dissolve like. That is how it works. So that's why, believe it or not, soap is actually made from oil. Cooking oil, or when you see, like, have you ever heard of the soap called palm olive? It was originally made from palm oil and olive oil. So there we go. That is why it can dissolve lipids. So like dissolves like, so this means that a lipid soluble molecule can go straight through the plasma membrane. Carbon dioxide, oxygen and water can also go straight through. Okay, simple diffusion. It follows a concentration gradient. Facilitated diffusion, we've talked about this already, but it's where there's no, specifically for this, there's no energy involved. So it can be a very simple channel, or it can be that it actually binds to something by binding to it, like a channel protein, or in this case a carrier protein. By binding to a carrier protein, the physical shape of it changes, and hence it can allow it through. And when it releases, it will open up again. Okay, so it's going with the concentration gradient through this carrier protein. It cannot go against it, because for that we need energy. Okay, we've talked about this already. There you can see, if you actually have a selectively permeable membrane and you have it set up like this in the lab, you can see that the one side will go higher than the other, which is really strange. But when you count the dots of water here versus the dots of water in this one, you will find that they are now equal on each side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, maybe, I hope I miscounted. Or maybe one is just going through. Anyways, the point is they are supposed to be in equilibrium, which means the same number of water molecules each side of the selectively permeable membrane. This is a video that I really want you guys to go and watch. It's called The Naked Egg, and you can find that on YouTube. I will actually post the link on the OLE for you. It really explains it really well. Once you have used acid to eat away the shell, then you have a membrane, a selectively permeable membrane on the inside of your egg that will either allow things in or out. And you can see here they took the water out, and over here they took some blue dyed water and took that in. And this is something that you can do at home as well. Okay, so these guys are called the science guys. Have a look at that. Okay, welcome back. Now, water potential, we talked about this. It actually applies to increase things. If we applied a physical pressure on this side, in other words, literally like a pump or a something, our selectively permeable membrane will then allow things to go through faster. Okay, but it always, you can see there's so much more water on this side than on that side, so it always wants to go from an area of high water potential to an area of low water potential. Okay, and the reason for that difference is because of these dissolved solutes. Alright, I feel like I'm repeating myself all the time, but when you look at red blood cells, if you have an isotonic solution, iso means it's the same on the inside as what it is on the outside, isotonic. So that is like saline we talked about earlier that people with contact lenses use. So if there is a 9% or 0.9% solution on the outside, there's a 0.9% solution on the inside, and water can go freely through, but it will always remain in equilibrium. So the cells remain nice and the way that they're supposed to look, which is this biconcave shape. In a hypotonic solution, guys, these words, hypertonic, hypertonic, and isotonic, always refers to the solution, not the inside of the cell, the solution. Okay, so hypotonic, hypo is low. Okay, hypo is low, hypo is low. So there's a low concentration of solute, a low concentration of solute, meaning this is where you take a cell and you put it into pure water. Now in that pure water there's nothing that is dissolved in it, so you have a very high water potential. And inside the cell you have a lower water potential because there's so much more dissolved salts and sugars and stuff inside the cell and proteins. So where's the water going to go? It's going to go from an area of high water potential to an area of low water potential. So a hypotonic solution has got very little dissolved solute. Hypertonic, on the other hand, is where we have a very high amount. So if somebody is hyper, they have a high level of energy, don't they? Okay, so a high level of dissolved stuff in our hypertonic solution. So this could be the same way that, for instance, we preserve a lot of things. If you are making, I love to use the example of biltong because I love biltong, is we actually take salt and you put it on the outside of the meat, and then the water goes from an area of a high water potential inside the cell because there's less dissolved stuff in there to an area of lower water potential or higher concentration of solute. So it will go out of the cells, and that is then how you actually kill and preserve the bacteria. We do this with a lot of things. Think about canned peaches or pickles. If you have gherkin pickles, they are in a solution that is very acidic and quite sweet. So your dissolved solute on the outside of those pickles are a lot higher than inside the cell. So the water will move from inside the cell where there's a higher water potential to the outside of the cell. Okay, and your cells shrivel up and die. Over here they burst because the water is flowing in. Here they are flowing out. When we look at plant cells, we did this the other day. Okay, so isotonic is where they are quite happy, the water is flowing in and out, in and out, in and out. But I showed you under the microscope when we put it in a salt solution, in other words, there's a low water potential on the outside and there's a high concentration of solute, in that case it was salt on the outside, the water will flow from where there's a high water concentration to a low water concentration. You can see the cell wall remained in place just like our picture did, and the water then streamed out of it, and the cell membrane actually pulled away from the edges. Then when you go to hypotonic, it means there's too much water, not enough dissolved solutes. So what's going to happen is the water will push into where there's a lot more solute. Okay, so it goes from an area of high water concentration to an area of low water concentration. So the water will come in. Okay, so you can see how it's bulging, and that is in a hypotonic solution. Here you can see it again, red onion cells, and they're nice and plump and very happy. So that is a isotonic solution, and then we added salt to it, and look how they pulled away from their cell walls. You can see they all went away because the water left the vacuoles and went into the salt solution because it's trying to create equilibrium. So please consider the following: surface area and diffusion. Look at these three blocks and tell me which one will have diffusion penetrate deeper into its center than the others. Obviously the small one, and that's why cells like to be small. Because they're small, it is very easy for them to then have stuff diffuse into them, or osmosis, or pumped into them even with active transport, but then they don't have to pump it around within the cell. which saves a lot of energy. So if you consider that, it basically, we talk about that as a surface area to volume ratio. This is my surface area, and there's 6 sides of it, and the volume is obviously what it makes up. So let's look at these 3 blocks. This is a 1 centimeter block, 1 centimeter by 1 centimeter by 1 centimeter. This one is 2 by 2 by 2. This one is 3 by 3 by 3. So our volume, if we compare that, the volume of the 1 centimeter block is 1 by 1 by 1, which gives us 1 cubic centimeter. 2 centimeters gives us 8 cubic centimeters, and 3 centimeters gives us 27 cubic centimeters. But look at our surface area. The first one, we take 1 by 1, so that's 1 times 1 gives us 1, and there's 6 of them, so 6 times 1 cubic centimeter gives us a 6 cubic centimeter. When we look at the second one, 2 by 2 gives us 4 cubic centimeters, and there's 6 of them, so that's 24 cubic centimeters. And this one is 3 by 3, which gives us 6 times 9 cubic centimeters is 54. So what is our ratios? This one is easy, 6 to 1. That is a very good surface area to volume ratio. Whereas this one is 24 to 8, or translates to 3 to 1. So it's basically half of that. And this one is 2 to 1. So as you can see, not very good surface area to volume ratio. So we want the surface area to volume ratio to be as big as possible. Okay, so you can see this, how the pink dye basically penetrated into these agar cubes. And by simply doing that, you can see this surface area to volume is ideal. This one, the volume that didn't get any of the dye due to diffusion, is obviously a lot smaller than this. So you can see how this works in practical terms. That's why cells like to be small, as I said earlier. Look at these two. The shape can also make a difference. Okay, both of these blocks have a volume of 27 cubic centimeters, but look at the surface area. This one is 3 by 3 multiplied by 6 basically gives us 54 centimeters squared, and its volume is 27. So 54 to 27. Yeah, okay. It's basically a 2 to 1 ratio, isn't it? Look at this one. Our surface area works out to 71 square centimeters to 27. So 54 to 27 versus 72 to 27. So just by changing your shape and increasing your surface area gives you a much better chance of running successful diffusion and osmosis. Okay, thank you for your attention. I will place some work for you on Education Perfect just to make sure you guys understand all of this. Thanks again. Okay, bye-bye.